Today I'm going to be talking about the calorimetry experiment. This experiment is broken up into three parts. The first part is the reaction between sodium carbonate and hydrochloric acid to give you two salt molecules, water and CO2. We are interested in how many moles of the limiting reagent will react, and we're interested in the amount of heat that will be released. We will do the calculations to determine the limiting reagent, but we also will do the calculations to determine how much of the heat was absorbed by the water. The amount of heat absorbed by the water in this reaction is the amount of heat that the reaction gave off. In the second part, we're going to take sodium hydroxide and HCl to give us sodium chloride and water again, and we're going to repeat the same process. And in the third part, we're just going to take solid sodium carbonate, put it in water, and it's going to go into solution, and we're going to repeat the same process. The third part, there is no limiting reagent because there is only one reagent. We are going to determine the amount of heat that's released in part one of this reaction. Remember, we're taking sodium carbonate solid, putting it in a hydrochloric acid solution. We're going to get sodium chloride, water, and CO2. To find out how much heat is released, we're going to have to use the specific heat of water to determine how much energy water absorbed. As you know, specific heat equals joules over grams times delta T. If we isolate the joules, here, joules would equal specific heat times grams times delta T. This is for the water. This is for the water. Now we're going to make two assumptions here. The first assumption is the specific heat for water is the same for all the solution, which is 1.184 grams divided by, joules divided by grams divided by Celsius. The other assumption is we're going to make is the density of all the solutions is 1 gram per milliliter. We will need to make these two assumptions to determine out the amount of heat that the water absorbed. Calculations for part 1, the amount of heat released. Remember, joules, or the amount of heat released, equals the specific heat of the water times the grams of the water times the delta T, the change in temperature of the water. Specific heat, as you recall, is 4.184 joules divided by grams divided by Celsius. We are using 30 milliliters of solution. Since the density of the solution is 1 gram per milliliter, you will be able to calculate the grams of solution. This will be the first question on the quiz. You see the number, you open up the quiz, you put in the correct answer there. Notice how the milliliters of solutions left, and you're only left with grams. Now, in this experiment, I started at 20.55 degrees Celsius. My final temperature was 27.20. You should be able to figure out the change in temperature. So joules equals 4.184, that is the specific heat, times the grams, times the temperature change. So this will end up being question 3. Notice how the grams cancel, Celsius cancel, and you're only left with joules, and joules is what you want to be left with. So you should be able to answer question 3. This is the amount of energy given off during the reaction. This will be positive number. This will be a positive number because the water absorbed the heat. You need to change the sign because the reaction gave off the heat. Now we're going to determine the number of moles that reacted. Since we're going to determine the amount of energy that reacted per mole, we need to determine the number of moles. In the previous slide, we determined the amount of energy. So we have the reaction, sodium carbonate plus 2 HCl gives me 2 sodium chlorides, water, and CO2. Now determine the limited reagent. You must pick one reagent. And I just picked one product, and I just picked CO2 as the product. First, determine the limited reagent using CO2 as the product. Okay, I weighed out 3.0 grams of this sodium carbonate. I divided it by its molar mass. The molar mass is very simple to calculate. You just add 2 sodium, 1 carbon, and 3 oxygens. Now, this first step, I'm at moles of sodium carbonate. Now, I know that sodium carbonate, for every 1 mole of sodium carbonate, I have 1 mole of CO2. So I go from 1 mole of sodium carbonate to 1 mole of CO2. That gets me to moles of CO2. And then I'll calculate that, and that'll be your answer to question 5. Now I'm going to do the same thing to the other reactant, which is the HCl. Well, first of all, let me cancel the grams. The moles of sodium carbonate, and I'm only left with moles of CO2. All right. Now, I have 30 milliliters of HCl. That's how much I added to the reactant. It was molarity on the label was 2.0 molar, which means for every 2 moles there is 1 liter. So first let me go to liters. 10 to the third milliliters is 1 liter. So at the first step I went from milliliters to liters. Next I'm going to go from liters to moles because this is the molarity. I know for every 1 liter of the solution I have 2 moles of the HCl. So now I'm at moles of HCl. Well, I know for every 2 moles of HCl I have 1 mole of CO2. So the 2 moles of HCl will go on the bottom. The 1 mole of CO2 will go on top. And I will be able to cancel the moles of CO2. Now the milliliters cancel, liters cancel, moles of HCl cancel. The only thing I'm left with is moles of CO2, and that's the only thing I want to be left with. The smaller one of these 2 numbers represents the limiting reagent. That is the number that will be used in the calculation. Now we're going to determine the amount of heat released in joules per mole. We'll take the energy released by the reaction, divide it by the number of moles of the limiting reagent, and that's going to give us the amount of energy released per mole. So if you do the calculations here, you're going to get joules per mole. That'll be question 7. Now I want to convert it to kilojoules, and all I have to do is multiply it by 1 over 10 to the third joules, 1 kilojoules by 10 to the third joules, and that'll give me kilojoules per mole. So this is the answer we're looking for the first reaction. You see how the joules cancel out. Now we did the first part. Now we're going to do the second part here. That's sodium hydroxide plus HCl. Give me sodium chloride plus water. Alright, so in part 2, the same thing. We have the reaction here. We have the specific heat. We have the joules, right, equals specific heat times grams times delta T. Same assumptions, right? Water has a specific heat of 4.184, and then all solutions have a density of 1 gram per milliliter. Same assumptions as experiment 1. Now we're going to calculate the amount of heat released for part 2. Once again, we know the joules equals specific heat times grams times delta T. Specific heat for water would be 4.184 joules per gram per Celsius. Now we use 50 milliliters of water, 25 from the HCl, 25 from the sodium hydroxide, a total of 50. So to find out the grams, we just multiply it by the density, and that will be your answer for number 9. Next, we're going to find out the temperature change. If I began at 20.55, it raised to 27.39, I'll find out delta T. That will be the answer to question 10. The joules are going to equal 4.184, right? You know, joules divided by grams by Celsius. It will be 50 grams, and then the temperature change is 6.184. That will give me the number of joules. Okay. Notice the units cancel out very conveniently. The grams cancel out, the Celsius cancel out. And the only thing I'm left with is joules. And joules is the only thing I want to be left with. Joules will be the only thing I want to be left with. This is the amount of energy given off during this reaction. Remember, this will be positive because the water absorbed that amount of energy. Where did it get that amount of energy? From the reaction. That number will be negative. So, determine the amount of moles of reactants. First of all, we determined the amount of energy in the previous slide. Now we're going to determine the amount of moles. We have the balanced equation, 1, 1, 1, and 1. Then we need to pick out a limiting reagent. Well, I'm just going to pick out water this time. Okay. I started off with 25.0 milliliters of sodium hydroxide. I want to convert that milliliters of sodium hydroxide to liters, so I know 10 to the third milliliters is 1 liter. So in this first step, I went from milliliters to liters. The next thing I want to do, I want to convert it to moles. How do I do that? Well, if I know the volume, I know the molarity. The molarity for the sodium hydroxide on the label in the experiment was 1.0, so I know I have 1 mole for every liter. And I know I have 1 mole of sodium hydroxide for every 1 mole of water. So this gives me the moles of water. I went from milliliters to liters of sodium hydroxide, liters of sodium hydroxide to moles of sodium hydroxide, moles of sodium hydroxide to moles of water, and that will be answer 12. Now I'm going to do the same thing for the HCl. I will do the same thing for the HCl. First of all, milliliters to liters. Then, since the HCl, the label on the experiment was 2 molar, for every 1 liter of solution I have 2 moles. And then for every 1 mole of HCl, I have 1 mole of water. This will give me the number of moles of water. So whichever one of these is the smallest, that is your limiting reagent. Whatever one of those is the smallest is your limiting reagent. Notice the milliliters cancel, the liters cancel, moles of HCl cancel, and only left with moles of water. So, to determine the amount of heat released in joules per mole, I take the energy released by the reaction, divide it by the moles of the limiting reagent, and when I divide them out, that will give me the moles, right, the joules per mole for the reaction. Remember, this is going to be a negative number because the previous page was a positive number. Why? Because the water absorbed that energy. It got hotter. When you get hotter, you gain energy. It had to get the energy from somewhere. It got the energy from the reaction, which lost that exact amount of energy. Now I'm going to take that number and I'm just going to convert it into kilojoules per mole. And that will be question 14, and that will be question 15. And you notice that the joules cancel out. So part 3 is we're going to be taking solid sodium carbonate and we're going to be putting in water, and it's going to go into solution. So we're going to get the amount of energy released from that reaction. Alright, same thing, specific heat's the same, joules is the same assumptions. Alright, so we're going to take the joules, which is specific heat, times grams times delta T, and once again specific heat's 4.184 joules per gram per Celsius. And this time we're using 25 milliliters of water, so you should be able to figure out the grams of the water. Milliliters of solution cancel, and we started at 20.55 Celsius and we ended up 25.8. You should be able to figure out the delta T. And to find the joules, we're going to take the specific heat of water, the grams of water, the change in temperature of the water, and that'll give us the joules. So you have questions 16, 17, and 18 on this slide. And you notice the units cancel out conveniently, and you're just left with joules, and joules is what you want to be left with. This, once again, is the amount of energy given off during the reaction. So the reaction itself gave away this energy. So when we find out the amount of energy that was released from the reaction, once again, it'll be negative. Alright, so in part 3, we have to find the moles, which is simple because there is no limiting reagent. There is no limiting reagent. It's just the moles of the sodium carbonate. Okay, so that's wrong. We don't have to do it. First determine limiting reagent using this. This is wrong. So all I need to do is say, okay, I got 3 grams of the sodium carbonate. I'm going to divide it by its molar mass. This is going to be in moles of sodium carbonate. That is the limiting reagent. It's the only reagent used. Grams cancel, and you're at moles of sodium carbonate. Now, determine the amount of heat released in joules per mole. First, as we did the other 2 prior experiments, the amount of joules divided by the amount of moles, and that'll give us the amount of energy released for that reaction. We're just going to convert it to kilojoules, and the final will be kilojoules per mole. So that'd be 20 and 21. Joules cancel out. Now, we have all 3 experiments here, okay? And we need them to equal this experiment. This is the whole idea of the experiment. You're taking these 3 individual reactions, you're going to manipulate them so they're going to equal this reaction, and we'll be able to find out the delta H for this reaction. So if we look at the blue, the first reaction, okay, let's see. All right, let's see, CO2. Well, CO2 is on the product side, and it's on the reactant side. So the first reaction we're going to have to reverse. Now when you reverse it, you just flip the sign. You flip the sign of the delta H. The second reaction, I say, okay, I got sodium hydroxide, and I have 2 sodium hydroxides here, so I'm going to have to multiply that by 2. Okay, so the first reaction, as I said, I just reversed it. Okay, the second reaction, you're going to have to multiply by 2, and when you do that, okay, you're going to also have to multiply this by 2. So the first one, you reverse it, which just means you switch the sign here. So whatever this answer was, you just switch the sign. This one you multiply by 2. And the third one you don't do anything to. You leave the same. And when you add them all up, let's do it. Okay? So, let's see. 2 sodium chlorides cancel, 2 sodium chlorides cancel. 1 water cancels, so 1 water will cancel, and I'll be left with 1 water. Solid, now it's solid sodium carbonate is on the product, solid sodium carbonate is on the reactant, so they cancel. Okay, so 2 HCl's cancel. So what am I left with? I'm left with 2 sodium hydroxides, 1 CO2, 1 sodium carbonate aqueous, and 1 water. So remember, this number, we change the sign. This number we multiply by 2. This number remains the same. And when you add them up, you're going to get the kilojoules per mole for this reaction here. And this was the whole point of the experiment. We want to determine this kilojoules per mole of this reaction without doing the reaction. And that's what we did. We did the 3 reactions here. We manipulated them. So when we add them all together, we get this reaction. Then you have to add the new kilojoules per mole for each reaction to get the final reaction. So this is the whole idea of the experiment, is to come up with this number and compare it to the actual number. Alright, so fill in all the numbers. Fill in all the numbers. Do your own data sheet and turn that in next lab.